The surface of the Earth presents an illusion of absolute stability and geological silence that governs every aspect of human perception. When walking through a dense forest or across an open field, the sensory input suggests a world of cold stone, damp soil, and inert minerals that have remained unchanged for eons. The ground is perceived as a solid, dead foundation upon which life is built, a mere stage for the biological and atmospheric processes that define the human experience. However, this perception of terrestrial passivity is a fundamental misunderstanding of the physics governing the planet. Beneath the soles of every pair of shoes and under the foundations of every skyscraper, a relentless and titanic nuclear process is unfolding with a complexity that rivals the internal mechanics of a star.
The Earth is not a cooling relic of a violent cosmic past, but a functioning, high-output, planetary-scale nuclear reactor that has been operating continuously for over 4.5 billion years. This internal furnace provides the kinetic energy required to shift continents, trigger the massive release of pressure through volcanic eruptions, and maintain the very structural integrity of the global environment. Approximately 50% of the total heat flux emanating from the interior of the Earth is generated not by the residual energy of the planet's formation, but by the ongoing radioactive decay of heavy elements, with element 92, uranium, serving as the primary fuel for this geological engine. The magnitude of this energy release is difficult to quantify within the standard metrics of human engineering. The Earth emits approximately 44 terawatts of heat into space, a staggering amount of energy that would, under normal thermodynamic laws, result in a frozen and geologically dead world within a few 100 million years if it were not being constantly replenished.
Lord Kelvin, one of the most brilliant physicists of the 19th century, famously miscalculated the age of the Earth as being between 20 and 40 million years because he viewed the planet through the lens of classical cooling, unaware that a hidden internal source of energy was counteracting the loss of heat. The discovery of radioactivity at the end of the 19th century completely overturned the biological and geological understanding of time, revealing that the Earth possessed a forbidden source of warmth. Uranium, specifically the isotope uranium-238, acts as a long-term thermal battery. As these heavy, unstable nuclei spontaneously break apart into lighter elements, they release alpha particles that collide with the surrounding silicate and metallic structures of the mantle and crust. This microscopic kinetic bombardment is converted into macroscopic thermal energy, creating a perpetual state of convection within the Earth's interior. Without this radiogenic heat, the mantle would solidify, and the tectonic plates would lock into a permanent, immovable shell. The implications of a cold, non-radioactive Earth are visible in the desolate landscapes of Mars. While Mars was once geologically active and possessed a thick atmosphere, its smaller mass allowed its internal heat to dissipate far more rapidly than that of the Earth. Once the internal radioactive furnace of Mars cooled below a critical threshold, the convection in its liquid outer core ceased, leading to the collapse of its global magnetic field. Without the shielding provided by a magnetosphere, the solar wind stripped away the Martian atmosphere, turning a potentially habitable world into a frozen, irradiated desert. The existence of every ocean, every breath of oxygenated air, and every living organism on Earth is directly tethered to the presence of uranium deep within the planetary structure. It is the invisible architect of the magnetosphere, the force that generates the protective bubble shielding the biosphere from lethal cosmic radiation. The planet remains a vibrant, geologically alive entity, only because element 92 continues its slow, multi-billion-year transformation towards stability. The very minerals that are often viewed with fear and trepidation due to their association with modern warfare and industrial disasters are in fact the same substances that prevent the Earth from becoming a frigid, lifeless tomb in the vacuum of space.
This planetary nuclear process is not merely a diffuse background event. It has, in the distant past, concentrated into natural fission reactors that mimic the design of modern power plants. In the Franceville Basin of Gabon, Africa, approximately 2 billion years ago, deposits of uranium reached a critical mass and started a self-sustaining nuclear chain reaction.
These natural reactors, known as the reactors, operated for hundreds of thousands of years, moderated by groundwater and regulated by the laws of nuclear physics long before the first human ancestor walked the plains. This evidence confirms that the Earth's relationship with nuclear energy is not a modern imposition of human technology, but a fundamental characteristic of terrestrial existence. The transition from viewing uranium as a geological necessity to an industrial asset represents the most significant shift in human capability since the mastery of fire. Humans have reached into the planetary basement, extracted the very fuel that keeps the world warm, and attempted to harness its density for purposes ranging from global electrification to total annihilation. The curiosity surrounding this element stems from its dual nature as both a creator of planetary habitability and a potential harbinger of technological destruction. The dense silvery white metal possesses a power density that defies common intuition, where a single gram of the material contains as much latent energy as several tons of fossil fuels. This realization has forced a re-evaluation of what is considered natural and what is considered synthetic in the realm of power. The human race is currently engaged in an unprecedented experiment to see if it can safely manage the same forbidden flame that drives the movement of the continents. Understanding the mechanics of uranium is not an elective academic exercise, but a necessity for understanding the past and future of the species. To ensure that the narrative of human progress does not enter its own period of terminal decay within the digital algorithms, the support of the audience through interaction is vital.
Engaging with the content by subscribing to the channel and providing a comment with the phrase "forbidden fruit" assists in maintaining the reach of this educational exploration, ensuring that the complex story of the elements remains accessible. The journey from the core of the planet to the center of the atom reveals a reality where the most dangerous material in existence is also the most essential for the survival of the global ecosystem. The density of facts surrounding uranium-238 and its decay chain provides a window into the deep time of the universe. The half-life of this isotope is approximately 4.5 billion years, a duration that almost exactly matches the current age of the Earth. This is not a coincidence, but a selection effect of planetary evolution. If uranium-238 decayed significantly faster, the Earth's internal engine would have run out of fuel long before complex life had the opportunity to evolve. Conversely, if it decayed slower, the heat output might have been insufficient to maintain the liquid state of the outer core. The precision of this radioactive clock governs the pacing of evolution itself, as the stability of the environment is predicated on the steady, predictable release of energy from the crust and mantle. The transition of uranium through its various daughter isotopes, including thorium, protactinium, and radium, eventually culminates in the creation of lead. This process is a one-way street of elemental transmutation, a slow-motion alchemical descent from the pinnacle of atomic complexity to the inert stability of element 82. In the context of the modern world, this geological perspective shifts the way we view raw materials. A piece of uranium ore is not just a rock. It is a concentrated fragment of the primordial conditions that allowed the solar system to form. It is a material that challenges the boundaries of chemistry and physics, existing at the very edge of what nature allows to remain stable.
When a geologist uses a Geiger counter in a mountainous region and hears the rhythmic clicking of the device, they are listening to the heartbeat of the planet. They are detecting the same energy that drives the mid-Atlantic ridge apart and pushes the Himalayas toward the sky. The heat generated by these subterranean nuclear reactions creates the temperature gradients necessary for the circulation of the Earth's mantle, which in turn acts as a conveyor belt for the crustal plates. This cycle of subduction and volcanic outgassing is what recycles carbon dioxide, regulating the global climate over millions of years and preventing the, quote, 7 effect seen on Venus or the, quote, 8 of Mars. The technical mastery required to move from the passive observation of these facts to the active manipulation of the uranium nucleus is the defining hallmark of the atomic age. We have moved from a species that simply lives on a nuclear-powered planet to a species that can build its own versions of that planetary core. However, the scale of this power is so vast that it necessitates a complete restructuring of safety, ethics, and engineering. The energy contained within the atomic bonds of uranium is millions of times greater than the energy found in chemical bonds, such as those in TNT or gasoline. This jump in magnitude is why the material is treated with a level of caution and reverence that borders on the religious. Every gram of this element is a reminder of the violent cosmic events that created it, events so energetic that they dwarf the power of our sun. The story of uranium is the story of how a quote, _9__, found in the dirt became the key to understanding the origins of the Earth and the potential for the eventual expansion of humanity into the stars. It is the bridge between the deep geological past and an uncertain technological future, a material that remains as enigmatic as it is essential. The internal structure of a uranium atom is a study in tension.
With 92 protons packed into its nucleus, the electromagnetic force pushing those positive charges apart is nearly overwhelmed by the strong nuclear force holding them together. It is a, quote, 10 of matter, waiting for a trigger to release its stored potential. In the natural environment, this release happens through the slow, random process of radioactive decay, contributing to the Earth's thermal budget. In a controlled environment, such as a nuclear reactor, humans provide that trigger, inducing a cascade of fissions that releases the energy in a concentrated burst. This transition from natural decay to induced fission is what allows us to generate gigawatts of electricity from a relatively small amount of material. Yet, the material itself remains unchanged in its fundamental properties. Whether it is heating a tectonic plate or a steam turbine, the physics remains consistent. It is an objective, mathematical reality of the universe that certain heavy elements are destined to break apart, and our survival has depended on being in the right place at the right time, with the right amount of uranium beneath us to keep the fire burning.
As we look deeper into the composition of the Earth's crust, we find that uranium is actually more common than several other familiar metals, such as silver or mercury. It is widely distributed, appearing in trace amounts in most rocks and even in seawater. This ubiquity means that the quote, _11____ nature of our world is not localized to a few mines or power plants. It is a global phenomenon. Every mountain range and every seafloor is a participant in the radiogenic heating process. The very soil that produces our food contains minute quantities of the element, contributing to the natural background radiation that has been a constant companion to life since its inception. This realization demystifies the element, removing it from the realm of science fiction and placing it firmly in the category of essential geological components. The quote, _12__, nature of uranium is a human construct, born of our fear of its destructive potential and our awe of its power. To the Earth, however, uranium is simply a fuel, a source of kinetic and thermal energy that ensures the continuation of the planetary cycle. It is the catalyst for the dynamism of our world, the reason why the Earth remains a place of constant change and renewal, rather than a static, frozen orb. The final consideration in this introductory block is the relationship between uranium and the concept of quote, _13____. When we discuss the energy of the Earth, we are discussing timescales that are almost incomprehensible to the human mind. The uranium-238, currently decaying in the mantle, was forged in a cosmic explosion that predates the birth of the Sun. It has been traveling through space, incorporated into the protoplanetary disk, and sunk into the Earth's interior over billions of years. Its presence is a link to the very beginning of our solar system, a physical witness to the formation of the planets.
When we use it today, we are tapping into a reservoir of energy that has been preserved for eons. The responsibility of handling such a material is immense, as we are interacting with the fundamental operating system of the universe. The following blocks will explore how this cosmic heritage was forged in the hearts of dying stars, and how human curiosity transformed a Victorian-era curiosity into the most potent force in our technological arsenal. The story of Element 92 is the story of humanity coming to terms with the raw power of the cosmos, hidden in plain sight within the stones of our own world. The positioning of uranium at the edge of the naturally occurring periodic table represents a fundamental threshold in the architecture of matter. As Element 92, uranium occupies a unique status as the heaviest primordial element that exists in significant quantities on Earth, effectively serving as the boundary between the stable building blocks of the universe and the fleeting, synthetic monsters of the transuranic series.
To understand why uranium exists at all requires an investigation into the extreme astrophysical environments that transcend the capabilities of standard stellar evolution. While common elements like carbon, oxygen, and even iron are forged within the pressurized, incandescent cores of active stars through the process of nuclear fusion, uranium is a product of absolute cosmic catastrophe. The internal temperatures and pressures of a star like the Sun are sufficient to fuse hydrogen into helium and eventually build elements up to iron. But the nucleosynthesis of heavier atoms presents a thermodynamic wall that ordinary stars cannot climb. Because the fusion of elements heavier than iron consumes more energy than it releases, the standard evolutionary path of a star provides no mechanism for the creation of element 92. Consequently, every atom of uranium found in the Earth's crust is a physical record of a violent event that occurred long before the formation of the solar system, originating in the rarest and most energetic phenomena in the known universe. The primary site for the creation of uranium is now understood to be the Kilonova, a gravitational collision between two neutron stars. Neutron stars are the collapsed remnants of massive suns, possessing a density so extreme that a single teaspoon of their material would weigh billions of tons. These objects are essentially giant atomic nuclei the size of a city, composed almost entirely of neutrons packed together at the limit of physical possibility. When two such entities spiral toward each other and collide, they release a gravitational and electromagnetic pulse that briefly outshines an entire galaxy. During this collision, a process known as rapid neutron capture, or the R process, takes place within a fraction of a second. In this high-energy environment, seed nuclei are bombarded by a flux of neutrons so intense that they grow in atomic mass faster than they can decay. This frantic accumulation of mass allows for the assembly of extremely heavy nuclei, including uranium, thorium, and gold. The Kilonova serves as the universe's heavy element factory, projecting these newly formed atoms into the interstellar medium at a significant fraction of the speed of light. This means that the uranium used in modern nuclear reactors is effectively fossilized energy from the collision of dead stars, representing a level of physical density and historical depth that defies standard human timescales. Once ejected from a kilonova, these heavy elements drift through the vacuum of space for millions of years, eventually becoming incorporated into the vast molecular clouds of gas and dust that serve as the nurseries for new solar systems. Approximately 5 billion years ago, one such cloud began to collapse under its own gravity, forming the Sun and the protoplanetary disk that would eventually become the Earth. Uranium, being a lithophile, or rock-loving element, did not sink entirely into the Earth's iron core during the differentiation process, but instead remained concentrated in the silicate-rich mantle and crust. This distribution is critical for the planet's subsequent geological history, as it placed the primary source of internal heat close enough to the surface to drive plate tectonics and volcanic activity. The uranium present in the Earth today is essentially a __17__ residue, a collection of heavy atoms that survived the chaotic assembly of the planet and have been slowly decaying ever since. Because the half-life of uranium-238 is roughly 4.47 billion years, approximately half of the uranium that was present at the birth of the Earth still remains, providing a continuous, multi-billion-year supply of radiogenic energy that sustains the planet's magnetic field and geological dynamism. The isotopic composition of uranium provides a precise window into the deep time of the galaxy, acting as a chronological marker for the age of the solar system. By measuring the ratio of uranium to its decay products, such as lead, geochronologists can determine the exact age of minerals within the Earth's crust and even the age of meteorites from the early days of the planetary disk. This science of radiometric dating is the foundation of our understanding of the Earth's history, allowing us to map the progression of life and the movement of continents with mathematical certainty. The presence of two primary isotopes, uranium-238 and the rarer, more unstable uranium-235, creates a dual clock system that cross-references itself, providing an internal check on the accuracy of geological measurements. Uranium-235 decays much faster, with a half-life of only 704 million years, which explains why it now makes up less than 1% of natural uranium. In the distant past, however, uranium-235 was much more abundant, making the natural environment significantly more radioactive, and even allowing for the spontaneous formation of the natural nuclear reactors in Gabon mentioned previously. The energetic potential of uranium is a direct consequence of its cosmic origin and its position on the edge of atomic stability. Because it was forged in the extreme pressure of a kilonova, the uranium nucleus is like a tightly wound spring, held together by the strong nuclear force, while the immense electromagnetic repulsion of 92 protons tries to tear it apart. This internal tension makes uranium the perfect medium for energy extraction. In a typical chemical reaction, such as the burning of coal or the explosion of TNT, energy is released by the rearrangement of electrons orbiting the nucleus. However, the energy stored within the nucleus itself, the binding energy that holds the protons and neutrons together, is several orders of magnitude greater. When a uranium-235 nucleus is struck by a neutron and undergoes fission, it splits into two smaller nuclei and releases a burst of kinetic energy and gamma radiation. This single event releases roughly 20 million times more energy than the combustion of a single carbon atom. This massive disparity in energy density is what makes uranium both a technological miracle and a profound strategic challenge, as it allows for the concentration of immense power within a very small physical footprint. The study of uranium also reveals the limitations of the universe's ability to maintain complex matter. Beyond element 92, the repulsive forces within the nucleus become so dominant that no element can exist for long periods in a natural environment. Elements like plutonium, neptunium, and americium, while they can be produced in stellar explosions or human reactors, decay so rapidly that they are not found in significant quantities in the Earth's crust. Uranium is the final __19_19__ waypoint in the periodic table, the last element that can withstand the test of billions of years of existence. This makes it a unique bridge between the permanent world of stable matter and the ephemeral world of radioactive transition. The fact that humanity has learned to manipulate this specific element is a testament to our understanding of the fundamental laws of physics. But it also places us in a direct relationship with the most violent events in the cosmos. We are, in a very literal sense, fueling our civilization with the debris of dead stars, utilizing the _20_ that were packed into the Earth's crust during its formation. Furthermore, the astrophysical journey of uranium highlights the interconnectedness of the microscopic and the macroscopic. The behavior of a single subatomic particle within a uranium nucleus is dictated by the same forces that govern the collision of neutron stars light years away and billions of years ago. The heat that warms the hands of a technician in a modern nuclear facility, or the power that illuminates a distant city, is the same energy that was once contained within the heart of a kilonova. This continuity of energy transfer from the most extreme environments in the universe to the mundane infrastructure of human life is one of the most compelling narratives in science. It removes the distinction between earthly and cosmic processes, demonstrating that our industrial and technological activities are merely a continuation of the thermodynamic cycles that have been operating since the beginning of time. Uranium is not just a metal. It is a physical manifestation of the universe's capacity for extreme events, a substance that carries the signature of the R process into the very heart of human civilization. As we consider the __23_ aspect of uranium, we must also recognize that we are living in a specific window of opportunity. As the isotopes of uranium continue to decay toward lead, the total amount of fissile material on the planet is slowly but inevitably decreasing. In several billion years, the natural __24_ of the Earth's crust will have diminished to the point where nuclear power, as we understand it, will no longer be possible using natural uranium. We are currently utilizing a resource that is, in every sense of the word, non-renewable on a cosmic scale. There is no process on Earth or within the Sun that can create more uranium. We are depleting a finite stockpile that was delivered to us at the birth of the world. This realization adds a layer of existential weight to our use of the element, as it represents a one-time inheritance of high-density energy that must be managed with a view toward the long-term survival of the species. The uranium in our minds is a dwindling legacy of a past that involved the destruction of entire suns, a thought that should instill a sense of profound responsibility in how we choose to deploy its power. In summary, the cosmic scale of uranium's history elevates it from a mere industrial commodity to a fundamental component of the universe's narrative. It is the heaviest natural element, a survivor of the most violent explosions in space, and the primary thermal engine of our planet. Its presence allows us to date the history of the world and provides us with a source of energy that is millions of times more concentrated than anything found in the biological or chemical realms. By understanding the origins of element 92 in the Kilonova and its subsequent integration into the Earth's geology, we gain a deeper appreciation for the delicate balance of forces that make life possible. Uranium is the ___25_ not because it is inherently evil, but because it is so potent, so ancient, and so intimately tied to the life and death of stars that its mastery requires a level of wisdom that humanity is still struggling to achieve. The following blocks will examine how this cosmic power was first encountered by humans, leading to a period of scientific wonder, medical tragedy, and the eventual realization that we had unlocked a force that could either sustain or destroy our world. The transition of uranium from a geological curiosity to a central protagonist in human history began not with a grand scientific breakthrough, but with the aesthetic demands of the 19th century European middle class. Long before the physics of the atomic nucleus were understood, uranium was primarily valued as a chemical pigment, capable of producing vibrant hues of orange, yellow, and a distinct ethereal green. This period, often referred to as the era of uranium glass or __26__, saw the integration of radioactive isotopes into the most intimate spaces of the domestic environment. Craftsmen discovered that the addition of uranium oxides to a glass melt resulted in a material that exhibited a striking fluorescent glow when exposed to ultraviolet light. This property, known as __27__, is a quantum mechanical phenomenon where the electrons of the uranium atoms are excited by high-energy photons and subsequently release that energy as visible light. Throughout the Victorian era, dining tables were adorned with plates, goblets, and decorative carafes that were, in a very literal sense, emitting low-level ionizing radiation. While the levels of radiation emitted by these household items were generally insufficient to cause acute harm, their presence illustrates a historical period of profound ignorance regarding the fundamental nature of the elements being manipulated for decorative purposes. The shift from chemistry to nuclear physics was precipitated by the discovery of radioactivity at the end of the 19th century, a period marked by the relentless intellectual labor of Marie and Pierre Curie. Their investigation into pitchblende, a dense and dark uranium ore, revealed a discrepancy that would alter the course of science. The ore itself was significantly more radioactive than the pure uranium extracted from it. This observation led to the realization that uranium is not a static entity, but a parent element that decays into a series of even more potent, 28 isotopes. The Curies spent years in a poorly ventilated shed, processing literal tons of industrial waste to isolate milligram quantities of these isotopes, specifically polonium and radium. The physiological toll of this work was immense and, at the time, entirely misunderstood. Marie Curie was known to carry test tubes containing concentrated radioactive solutions in her lab coat pockets, viewing the faint blue-white luminescence they emitted in the dark as a beautiful and benign curiosity. This __29__ was, in reality, a source of intense gamma and alpha radiation that was systematically dismantling the molecular structures of her cellular DNA. The journals she used to record her findings remain so highly contaminated over a century later that they are stored in lead-lined boxes at the Bibliothèque Nationale in Paris, requiring researchers to wear protective suits and sign waivers of liability before consultation. This era of scientific discovery was characterized by a tragic lack of shielding, as the concept of radiation protection did not yet exist. The pioneers of the atomic age were effectively operating in a state of biological blindness, unaware that the very materials they were celebrating as medical and scientific miracles were capable of inducing chronic radiation sickness and terminal leukemia. The eventual death of Marie Curie from aplastic anemia serves as a grim marker of the boundary between the age of chemical discovery and the age of nuclear reality. It established a precedent that remains central to the handling of uranium today. The element is an objective, uncompromising force that functions according to the laws of physics, indifferent to the intentions or the health of the observer. As the 20th century progressed, the focus shifted from the external radiation of uranium's decay products to the internal energy of the uranium nucleus itself, leading to the discovery of nuclear fission in 1938 by Otto Hahn, Lisa Meitner, and Fritz Strassmann. This discovery revealed that a single neutron, when absorbed by a uranium-235 nucleus, could cause the entire structure to become unstable and split apart, releasing a quantity of energy that was previously inconceivable in the realm of classical chemistry. The realization that uranium could be used to create a self-sustaining chain reaction led directly to the Manhattan Project and the development of the first atomic weapons. This period saw the most intense concentration of scientific talent in history, all focused on the task of enriching uranium.
separating the fissile uranium-235 from the more stable uranium-238. This process required the construction of massive industrial complexes, such as those at Oak Ridge, Tennessee, where gaseous diffusion and electromagnetic separation were used to sort atoms based on their infinitesimal mass differences.
The stakes of this work were highlighted by a series of criticality accidents that occurred during the experimental phases of the project. These events, often involving the manual manipulation of fissile material, demonstrated the thin margin between a controlled state and a lethal surge of radiation. The most infamous of these incidents involved a 6.2 kilogram sphere of plutonium, a transuranic element created by bombarding uranium-238 with neutrons, which earned the nickname the Demon Core, after it was involved in 2 separate fatal accidents at the Los Alamos laboratory. The mechanics of these accidents provide a chilling look at the physics of prompt criticality. In August 1945, physicist Harry Daghlian was performing a neutron reflection experiment, surrounding the core with tungsten carbide bricks to see how many were required to bring the material to the edge of a chain reaction. A single brick accidentally slipped from his hand and fell onto the core, instantly creating a critical mass that allowed a runaway sequence of fissions to occur.
In a fraction of a second, the core emitted a massive burst of neutrons and gamma rays, accompanied by a characteristic blue flash caused by the ionization of the surrounding air. Daghlian immediately disassembled the stack of bricks to stop the reaction, but the damage to his biological systems was already irreversible. He died 25 days later from acute radiation syndrome, a process characterized by the systemic failure of the hematopoietic and gastrointestinal systems, as the body's ability to produce new cells was completely destroyed by the radiation pulse. The second accident involving the same core occurred in May 1946, during a demonstration led by Louis Slotin. Slotin was using a technique known as tickling the dragon's tail, which involved manually lowering a half shell of beryllium over the core to reflect neutrons back into the center.
To prevent the shell from closing completely and triggering a chain reaction, he used the tip of a standard flathead screwdriver to maintain a small gap between the two components. During the procedure, the screwdriver slipped, the shell closed, and the core immediately went prompt supercritical. Witnesses reported the same blue glow and the wave of heat. Slotin used his hands to flip the shell off the core, stopping the reaction and likely saving the lives of the other 7 people in the room. But in doing so, he absorbed a lethal dose of nearly 1,000 rads of radiation. He died 9 days later in a state of agonizing physical decay, as the radiation had effectively cooked his internal organs at a molecular level. These incidents underscore the reality that uranium and its derivatives do not possess a will or a desire for vengeance. They are simply physical systems that react instantaneously to changes in their environment. The failure was not in the material, but in the human arrogance that assumed a common tool like a screwdriver could provide a sufficient safety margin for the most powerful force in the universe. The Demon Core accidents forced a total re-evaluation of how radioactive materials are handled, leading to the development of remote-controlled manipulators and the strict isolation of personnel from fissile materials during experiments. This transition marked the end of the heroic or cowboy era of nuclear physics and the beginning of a highly regulated, standardized approach to nuclear safety. It also solidified the cultural perception of uranium as a forbidden substance, a material that demands a level of precision and technological discipline that leaves no room for human error. The move from the Victorian dinner table to the lead-shielded laboratory represents a journey of increasing awareness regarding the invisible world of the atom. We have learned that the same properties that make uranium a useful pigment or a source of medical isotopes also make it a potential harbinger of catastrophic biological damage. The biological impact of uranium and its radiation is a study in microscopic destruction. When ionizing radiation passes through living tissue, it strips electrons from atoms, creating highly reactive free radicals that can sever the chemical bonds of the DNA double helix. If the damage is extensive enough, the cell loses the ability to replicate or repair itself, leading to cell death or the formation of cancerous mutations. This is the hidden cost of the atomic age, a realization that the energy we use to power our cities is derived from a process that is fundamentally incompatible with biological life in its raw form. This necessitates a permanent barrier between the nuclear process and the biosphere, a requirement that defines the architecture of every modern nuclear power plant and waste storage facility. The heavy lead glass, the meters of reinforced concrete, and the sophisticated filtration systems are all designed to manage the madness of the element, ensuring that the kinetic energy of fission is harvested without allowing the accompanying radiation to leak into the environment. Reflecting on this history, it becomes clear that uranium has acted as a catalyst for human maturity. It has forced us to develop global standards of safety, complex international treaties, and an unprecedented level of scientific cooperation. The element does not forgive negligence, and it does not respect political boundaries. The fallout from a nuclear incident can travel across continents, making the management of uranium a truly global responsibility. The drama of the 20th century, the Cold War, the nuclear arms race, and the disasters at Chernobyl and Fukushima is all centered around the challenge of controlling this single heavy metal. We have moved from a species that played with uranium toys to a species that holds the power of planetary extinction in its hands. The transition from the green fog of Victorian curiosities to the blue flash of Los Alamos represents the most rapid and dangerous learning curve in the history of our species. Uranium remains at the center of this tension, a silent witness to our attempts to master the cosmic fire that forged our world. The following block will explore how this forbidden power has been integrated into the hidden machinery of modern life, from the electricity in our homes to the armor on the battlefield, revealing that the atomic age is not a historical event, but our current, everyday reality. The integration of uranium into the structural and functional fabric of modern civilization is often invisible, yet it constitutes a fundamental pillar of contemporary technology and geopolitics. While the public consciousness often associates element 92 exclusively with massive cooling towers or the catastrophic imagery of the mid-20th century, the material is physically present in a surprising variety of mundane and specialized contexts. In the domestic sphere, the historical use of uranium as a pigment has left a tangible radioactive footprint in the form of antique ceramics and glassware. The most notable example is the radioactive red glaze used in Fiesta dinnerware produced prior to 1972, which utilized uranium oxide to achieve a brilliant orange-red hue. In these objects, the uranium atoms are embedded within a ceramic matrix, continuously undergoing alpha decay and emitting low-level gamma radiation that can be easily detected by modern instrumentation. Similarly, certain older industrial smoke detectors utilize specific radioactive isotopes to ionize the air within a sensing chamber, creating a small but steady electrical current that would be interrupted by the presence of smoke particles. Although modern consumer electronics have largely transitioned to different isotopes or optical sensors, the legacy of uranium's utility in precision instrumentation remains a testament to its unique physical properties. The most profound application of uranium in the 21st century is its role as the primary fuel for the global nuclear energy infrastructure. The efficiency of uranium as an energy source is dictated by the laws of nuclear physics, which provide an energy density that renders chemical fuels virtually obsolete by comparison. In a standard pressurized water reactor, the energy released from the fission of a single uranium-235 nucleus is approximately 200 million electron volts. To put this in a macroscopic context, the complete fission of 1 kilogram of uranium-235 produces as much energy as the combustion of approximately 2.7 million kilograms of high-grade coal. This massive disparity arises because chemical combustion relies on the rearrangement of valence electrons, whereas nuclear fission taps into the strong nuclear force that binds the nucleus itself. The process of generating electricity from uranium is, at its core, a sophisticated method of boiling water.
The heat generated by the controlled chain reaction in the reactor core is transferred to a primary coolant loop, which then passes through a heat exchanger to produce high-pressure steam. This steam drives massive turbines connected to electrical generators, converting the cosmic fire of the atomic nucleus into the alternating current that charges smartphones, powers industrial machinery, and illuminates cities across the globe. This conversion process represents the most efficient and carbon-neutral method of baseload power generation currently available to the human species, providing a continuous flow of energy that is independent of atmospheric conditions or the diurnal cycle. Beyond the generation of civilian power, the physical properties of uranium have made it an indispensable material in modern military engineering, particularly in the form of depleted uranium, or DU. Depleted uranium is the byproduct of the enrichment process. After the fissile uranium-235 is removed for use in reactors or weapons, the remaining material consists almost entirely of the more stable uranium-238. This metal is characterized by an extraordinary density of 19.1 grams per cubic centimeter, making it approximately 67% denser than lead and 2.5 times denser than stainless steel. In the context of ballistics, this extreme density translates into immense kinetic energy. When a depleted uranium penetrator is fired from a tank cannon, its mass allows it to maintain velocity and stability over long distances, delivering a concentrated point of pressure that can easily defeat the thickest composite armor. Furthermore, uranium possesses a unique metallurgical property known as self-sharpening. Unlike traditional tungsten penetrators, which tend to mushroom or flatten upon impact, depleted uranium undergoes adiabatic shear banding, where the edges of the penetrator fracture in a way that maintains a sharp, needle-like point as it bores through armor. Upon penetration, the pyrophoric nature of finely divided uranium dust causes it to spontaneously ignite when exposed to the oxygen-rich environment inside a vehicle, resulting in a devastating combination of kinetic and thermal effects. This same density makes depleted uranium an ideal material for defensive armor plating, where it is sandwiched between steel layers to provide a nearly impenetrable barrier against incoming projectiles. The utility of uranium extends far beyond the confines of the Earth's atmosphere, serving as the essential power source for the exploration of the outer solar system. For spacecraft traveling to the gas giants or into the interstellar medium, solar energy is an unviable option due to the inverse square law of light. At the distance of Pluto, sunlight is roughly 1,000th as intense as it is at Earth. To overcome this limitation, NASA and other space agencies utilize radioisotope thermoelectric generators, or RTGs. These __55__ do not rely on fission, but rather on the steady, predictable heat generated by the alpha decay of heavy isotopes, often plutonium-238, which is synthesized from uranium-238 in specialized reactors. The heat from this radioactive decay is converted into electricity through the Seebeck effect, utilizing thermocouples to create a voltage from the temperature differential between the hot radioactive core and the cold vacuum of space. This technology has enabled the most significant achievements in space exploration, including the Voyager probes, which have operated for over 4 decades and are currently the most distant human-made objects in existence. The Mars rovers, such as Curiosity and Perseverance, also utilize this quote, 56 to maintain their internal temperatures and power their scientific instruments during the frigid Martian nights and global dust storms that would otherwise render solar-powered vehicles inoperable. The presence of uranium in our lives is also a critical component of modern medicine, specifically in the production of medical isotopes. While uranium itself is not injected into patients, the neutron flux produced by uranium fission in research reactors is used to transmute stable elements into radioactive isotopes like technetium-99m. This specific isotope is used in tens of millions of medical diagnostic procedures every year, allowing physicians to visualize the internal functioning of organs, track blood flow, and detects the early stages of cancer or cardiovascular disease. Without the foundational technology of the uranium fuel cycle, the field of nuclear medicine would effectively cease to exist, depriving the global population of some of the most effective tools for non-invasive diagnosis and treatment. This application highlights the profound irony of element 92. The same atomic properties that enable the creation of the most destructive weapons in history are also responsible for saving countless lives through medical innovation. In the realm of high-end engineering, the density of uranium is utilized for stabilization and counterweighting in aerospace and maritime applications. Because it can provide the necessary mass in a significantly smaller volume than lead or steel, depleted uranium has been used as trim weights in the control surfaces of commercial aircraft, such as the Boeing 747, and in the keels of high-performance sailing yachts. In these roles, the metal is completely encapsulated to prevent any environmental exposure, serving as a silent, heavy sentinel that ensures the aerodynamic and hydrodynamic stability of complex machines. This application demonstrates that even when its nuclear properties are not being actively exploited, the sheer physical presence of the uranium atom, with its 92 protons and large number of neutrons, offers engineering solutions that no other naturally occurring material can provide. The environmental and strategic management of uranium remains one of the most complex challenges of the modern age. Because of its long half-life and the hazardous nature of its decay products, such as radon gas, the extraction and processing of uranium requires stringent environmental controls. Uranium mining involves the extraction of ores that often contain less than 1% of the actual metal, necessitating the processing of vast quantities of rock. The resulting quote 57 must be carefully managed the leaching of radioactive and heavy metal contaminants into the local water table. Similarly, the quote 58 of the nuclear fuel cycle, the management of spent fuel, requires a long-term commitment to geological isolation. Spent fuel remains thermally and radioactively potent for thousands of years, leading to the development of deep geological repositories designed to sequester the material from the biosphere for timescales that exceed the duration of recorded human history. These facilities, such as the Onkalo repository in Finland, represent some of the most ambitious engineering projects ever undertaken, intended to protect future generations from the radioactive legacy of the current technological era. The strategic importance of uranium has also reshaped global diplomacy and trade. The distribution of uranium reserves is highly concentrated in a few geographic regions, including Kazakhstan, Canada, and Australia, creating a geopolitical landscape where energy security is inextricably linked to the stability and cooperation of these nations. The International Atomic Energy Agency, IAEA, serves as the global quote 59 ensuring that uranium intended for civilian power generation is not diverted for the production of weapons-grade material.
This system of international safeguards is the only mechanism that prevents the proliferation of nuclear technology from destabilizing the global order. The complexity of these monitoring efforts, involving satellite surveillance, environmental sampling, and intrusive inspections, reflects the unique status of uranium as the only natural resource capable of fundamentally altering the balance of power on a planetary scale. Ultimately, the role of uranium in our lives is characterized by a state of __60__. It is the invisible architect of the modern energy grid, the silent driver of deep space exploration, and the uncompromising weight behind the most advanced military technologies. It is a material that forces us to think in timescales of millions of years and in distances of billions of kilometers. We have moved beyond the point of simply discovering the element. We are now entirely dependent on its properties to maintain the complexity of our global civilization. Every time a light switch is flipped, a medical scan is performed, or a distant planet is photographed, the __61__ of uranium is the silent partner in that achievement. The material itself remains indifferent to its various roles, continuing its slow, inexorable decay according to the fundamental constants of the universe, while humanity continues to grapple with the immense responsibility of wielding the power of the atom. The final block will examine the inevitable conclusion of this atomic journey as we follow the path of uranium through the eons toward its eventual transformation into lead, revealing the ultimate fate of the energy that currently powers our world. The internal tension that defines the uranium nucleus is not a permanent state, but a prolonged transition toward an inevitable thermal and structural equilibrium. Every atom of uranium-238 currently existing in the Earth's crust, or within a nuclear fuel assembly, is governed by a statistical certainty of transformation known as radioactive decay. This process is the ultimate expression of the second law of thermodynamics, which dictates that all concentrated energy and complex structures must eventually dissipate and simplify over time. For uranium, this journey is a multi-generational descent through a series of unstable __62__ isotopes, a sequence of elemental transmutations that will not cease until the material reaches the total stability of lead. This decay chain is a fundamental clock of the universe, a silent and relentless progression that began in the hearts of dying stars and will continue long after the biological and technological signatures of humanity have vanished from the planetary record. The path from element 92 to element 82 is a 14-step sequence of alpha and beta emissions, during which the original uranium atom sheds mass and energy, briefly becoming thorium, protactinium, radium, and radon, before finally settling into the inert, non-radioactive state of lead-206. This transformation is the thermodynamic __63__ that the matter has been seeking since its violent creation in a Kilonova explosion. In its original state, the uranium nucleus is overcrowded, possessing far more protons and neutrons than the strong nuclear force can comfortably hold against the repulsive electromagnetic push of 92 positive charges. By ejecting alpha particles, each consisting of 2 protons and 2 neutrons, the nucleus gradually lowers its internal energy and moves closer to the __64__ on the chart of nuclides. This process releases the kinetic energy that humans have learned to harvest for power, but for the element itself, it is a slow shedding of the __65__. The half-life of uranium-238, spanning 4.5 billion years, ensures that this process is one of the most gradual phenomena in nature, providing a steady baseline of energy that has defined the thermal history of the Earth. However,
The inexorable nature of this decay means that the planetary battery is slowly but surely running out of charge. There will come a point in the distant geological future when the concentration of uranium in the mantle falls below the threshold required to maintain the convection currents that drive plate tectonics.
When the internal nuclear furnace of the Earth eventually cools, the planet will undergo a profound transition from a dynamic, living world to a geologically dead one. The movement of the continents will cease, the volcanic outgassing that replenishes the atmosphere will stop, and the liquid outer core will solidify, leading to the final collapse of the global magnetic field. This eventual __quote_66_ of the planet is the macroscopic consequence of the microscopic decay of uranium atoms. Without the constant replenishment of radiogenic heat, the Earth will follow the trajectory of Mars and the Moon, becoming a cold, silent sphere of silicate rock and iron, its surface scourged by solar wind and cosmic radiation without the protection of a magnetosphere. In this context, the presence of uranium is the only thing standing between the current vibrant biosphere and a permanent, frozen state of planetary stasis. The energy that fuels modern civilization is merely a small diversion of this larger, terminal flow of heat from the Earth's interior to the vacuum of space. The final product of this long radioactive journey, lead, is the antithesis of the uranium that preceded it. While uranium is dense with potential energy and characterized by its instability, lead is the graveyard of nuclear energy. It is one of the most stable elements in the universe, possessing __67_ of protons and neutrons that create a perfectly balanced and tightly bound nucleus. Lead does not decay. It does not emit radiation. It does not change. It is the ultimate state of __68_ for heavy matter. The accumulation of lead in the Earth's crust is the physical evidence of the energy that has already been spent over the last several billion years. When geologists measure the ratio of uranium to lead in a crystal of zircon, they are looking at an hourglass where the sand of uranium has been falling into the basin of lead since the moment the crystal formed. This leaden silence is the destination toward which all heavy elements in the solar system are traveling. The massive power of the atomic age, the terror of nuclear weapons, and the promise of carbon-free energy are all temporary phenomena, mere noise in the long, slow transition from the fury of the Kilonova to the stillness of a lead brick. The human relationship with uranium is characterized by a profound temporal mismatch. The entirety of human civilization, from the first agricultural settlements to the most advanced quantum computers, has occupied a fraction of time so small that it is effectively invisible, compared to the half-life of a single uranium atom. We have emerged during a specific window of the Earth's history, where the concentration of uranium is high enough to be easily harvested, but has already decayed enough to allow for a stable environment. We are, in a biological sense, parasites at a fading fire, utilizing the last few billion years of a planetary engine that was ignited long before our species was a possibility. Our technological mastery of the atom is not an act of creation, but an act of acceleration. By inducing fission in a reactor, we are simply forcing the uranium to release its stored energy in a fraction of a second, rather than over billions of years. We are burning the cosmic inheritance of the Earth at a rate that is millions of times faster than the natural background of radioactive decay. This realization places the current nuclear debates into a much broader, existential perspective. The problem of nuclear waste, for instance, is a challenge of managing the afterglow of this accelerated decay. The spent fuel from a reactor contains isotopes that will remain hazardous for tens of thousands of years, a time span that dwarfs the stability of any human government or language. We are forced to design containment systems that can withstand the test of deep time, communicating the danger of these materials to future generations who may have no record of our civilization.
The repositories we build in the depths of the Earth are effectively artificial lead-in-waiting zones, places where we hope the matter can finish its journey to stability without interfering with the thin layer of the biosphere. The engineering of these facilities is perhaps the most honest acknowledgement of our place in the universe. We are a species that has learned to tap into the fundamental energy of matter, but we remain entirely subject to the long-term consequences of that energy's inevitable decay. In the ultimate timeline of the universe, the story of uranium concludes in a state of total entropy. Trillions of years from now, long after the last stars have exhausted their hydrogen fuel and faded into white dwarfs and black holes, the remaining radioactive elements in the cold husks of dead planets will finish their transformations. The forbidden flame will finally be extinguished. The universe will enter the degenerate era, a period where the only sources of energy are the slow decay of protons and the final settling of atomic nuclei. In this distant future, the fury and light of the atomic age will be nothing more than a faint memory in a universe dominated by black holes and cold, inert matter. The uranium that once powered cities and drove the movement of continents will have all become lead, heavy, grey, and dead. This is the leaden coffin of the cosmos, the state of maximum stability and minimum energy toward which the laws of physics have been pushing since the beginning of time. The study of element 92, therefore, provides more than just a technical understanding of energy and matter. It offers a profound lesson in the nature of reality. It reveals a universe that is fundamentally dynamic, yet ultimately bound by the laws of decay and simplification.
It shows that the most powerful materials in existence are also the most temporary in their state of high energy. We have spent the last century learning to manipulate the coiled spring of the uranium nucleus, believing that we had become the masters of nature. However, a closer look at the physics of the element suggests that we are merely observers of a much larger, much older process. We are using the energy preserves of a cosmic event that we can barely comprehend, and we are doing so at the very end of the universe's era of high energy complexity. The uranium in our reactors is a reminder that we live in a world of finite resources and absolute physical laws, where every joule of energy we extract must eventually be paid back in the form of entropy and decay. As the final atoms of uranium on a dying Earth eventually turn to lead, the story of our planet will reach its conclusion. The vibrant, tectonically active world that supported the evolution of life and the rise of technology will have completed its thermal mission. The __quote_82_ was the catalyst for everything we know, the air we breathe, the ground we walk on, and the power we use to illuminate our nights. It was the spark that allowed the Earth to remain a sanctuary in the cold vacuum of space. By understanding uranium, we understand the precariousness of our existence. We see that we are living on a giant nuclear-powered spacecraft that is slowly losing its ability to generate heat. Our task as a species is to use the remaining energy of this __quote_83_ to find a way to transcend our planetary origins, perhaps seeking out new __quote_84_ around other stars, or learning to master the even more complex physics of fusion. Ultimately, uranium is the ticking clock of the Earth. It measures the time remaining for our geological and biological world. It is the silent witness to the formation of the solar system and the ultimate judge of our technological wisdom. We have dared to open the __quote_85_ reservoir of the atom, and in doing so, we have tied our fate to the behavior of element 92. Whether this power leads to a future of unlimited expansion or to a sudden radioactive end is a question that depends not on the physics of the atom, but on the maturity of the species that wields it.
The uranium doesn't care. It will continue to decay, atom by atom, second by second, until it reaches the quiet stability of lead. We are the ones who must decide what to do with the light and heat it provides during its long journey home. The story of uranium is the story of the universe itself. A brief, brilliant flash of energy in an infinite sea of darkness. A forbidden flame that we have momentarily captured to light our way through the deep time of the cosmos. In the end, there is only the silence of the lead, a final, unchangeable period at the end of the long sentence of atomic history. This is the legacy of element 92, a material that gave us the world, and in doing so, told us exactly how it would end.